Alrighty, g'day everyone. I wanted to record this video for you guys tomorrow. This is now going to be Thursday lesson for you all. The reason I wanted to do this is just so that we're all up to date. We haven't missed any content so that we can also understand the experiment that we're going to do on Friday. Now, yesterday on Tuesday, we rushed through a whole bunch of content. We summarized a bunch of topics from waves, diffraction, refraction, reflection, and also a couple of the examples of evidence that we have for wave particle duality. And we finished on that last question on Snell's law. Now, the experiment that we're going to be doing is going to be using Snell's law to calculate the refractive index of a certain prism. Okay, we'll talk more about that on Friday, but I figured it would be appropriate for us to also just kind of understand the mathematics of that a little bit more, which is the point of this. So for today, I just want you guys to go through this at your own pace. And by the end of it, we'll get an understanding of both ray diagrams and Snell's law. So both of which are really important. Ray diagrams are basically just how we actually draw all of these different problems. And that's really important. When you guys are given all these different types of scenarios, the first thing you're going to want to do is draw the picture. All right, it's very hard to understand if you don't have some kind of visual aid there for you. So number one, draw it. The way that we do that is through ray diagrams. Now we've got two main things that occur. Number one, we have something that's reflected. All right, as the incident light comes in, it's going to be reflected. And we remember the angle of incidence is equal to the angle of reflection. All right, that's going to be the first thing you're going to want to do. So if it comes in at 50 degrees, you are assured that it's going to bounce off at 50 degrees as well. We've also got something being refracted into the new medium. So this might be air up here in yellow, and it might be water down here in blue. Okay, and that's going to be bent. It's going to be at a different angle, and we can use Snell's law to calculate that. Okay, so our laws of reflection, the incident, no, sorry, go back, no, wrong way, I've lost everything entirely. Okay, can't go back, never mind. That's not ideal. Sure. The last question was just a problem for you guys to do. That's all right, we can do this one instead. So here's a kind of problem that you might get. If you've got something coming in here, can you identify the angle of incidence, the angle of reflection, and then this angle Q? We aren't interested in the angle of refraction yet. We haven't learned Snell's law technically yet, so we don't know how to do that. Now, one thing that's really important is that the angle of incidence is next to the normal. I don't know if you can see that, so let me put in my laser pointer here. This is the normal. The normal is perpendicular to where the two mediums collide. So this one right here, that is the normal. We call this the normal. Okay, it's perpendicular to those two mediums right there. So it comes in and it reflects off, and then we have our normal in the middle. So that is our angle of incidence because it's next to the normal. Okay, so we can see that because these two are perpendicular, that's going to be 90 degrees between the two. So let's see if I can write that in. 90 degrees between here to here. So if this is 56, the angle of incidence must just be 90 minus 56, which if I can do my quick math, should be 34 degrees. So that's what our angle of incidence would be. And because we know that the angle of reflection is equal to it, then we also know that R is also 34 degrees. Okay, and then because of Q, well, I guess we've got some kind of Z law really happening going on here, but also from the corresponding angles, Q is going to be 56 degrees. But if you didn't know how to do that, you're not too familiar with your geometry, just do your 90 degrees between here and here. You know that R is 34, which means Q must be 90 minus 34, which is 56. Okay, so number one, draw your situation. The angle of incidence must be equal to the angle of reflection, and we'll come up to refractive angles shortly. Here's a couple of other trickier problems that you guys might want to do between two different mirrors. So we've got something coming in, all right, 25 degrees to here. You're going to have to draw the normal line and figure out what the angle of incidence is in there. You'll know the angle of reflection, and then you've got a couple of mirrors to see how it bounces off. Those are on slides 29 and 30, just a little bit more challenging for you. Okay, and if you want some more practice, even still on your ray diagrams, you can go to page 445 and do your check your learning. All right, but if you're understanding the basics of it, then we're happy to move on. All right, this type of situation is where we might be looking at a mirror. Okay, so we're not just looking at where is the light going. So sorry, I put my laser pointer on. We're not just looking at where is the light going. All right, so maybe a photon is being emitted from here. Mirror, there it is here. It hits the mirror. It hits the mirror. If we're trying to look at a mirror, we see the reflection of the mirror. We don't see the object itself. The object is here. We see it inside of the mirror. Now, the way that we can draw these type of situations is that number one, just like how the angle of incidence is going to be equal in a reflected mirror, okay, or a reflection, let's say we've got this, let's call it D, that's the distance from the bottom of the object to the mirror. That's going to be the exact same. It's reflected exactly. So those distances are the same. And the same thing is going to happen for the top. Let's call it D2. That's going to be the exact same as well. And that makes sense, right? It's being reflected. If that's 1 meter for D2, it must be 1 meter that we see inside of that mirror. Okay. I've definitely seen more for the year 12s. They'll ask questions like how far away would the object be? Well, you would have D2, maybe it's 1 meter, and you're standing 0.5 meters away. The question might be, how far away is the object? It would be the combination of your 0.5 for the mirror for you and its object reflection distance. So 1 meter, 0.5 plus 1, you would perceive it as 1.5 meters away. Okay, and same thing here, that we've got our angle of incidence equal to our angle of reflection, and very similar concept for our diagram on the right over here. Okay, so far what have we learnt? Angle of incidence is equal to the angle of reflection. The reflection distances are the same, not the same for refraction. I'll come to that soon. Okay, here's a nice simulation. So you can go to the PhET page. They do lots of different science simulations. And it'll allow you to change different kind of refractive properties. And the refractive index of 1, that's air. So maybe some light's coming from air and it's going into glass. And I'm encouraging you guys to just try out different angles. See what happens to both that reflected and refracted angle. Please don't spend too long on this. You can see it on slide 40 for you guys. But just to play around with, just to kind of get a more tangible experience with that. But this is pretty much what our experiment is going to be on Friday. Okay, we did speak about this a little bit. So if we've got a photon, right, that's coming in, maybe this is air. We call it a fast medium. What that means is that it's not very dense. There's nothing slowing it down. So the photon of light can go as fast as it possibly can at the speed of light. Okay, but then it might go into a slower, more dense medium. All right, water, for example, just like how you're walking in water, all right, you're going to be slowed down. So is light, all right, and it's going to bend. Instead of going at the normal angle, it slows down and it bends. But once it goes back into that faster medium, it shoots off again at that same normal angle. You can kind of see that here. All right, so once it goes into that slower medium, the dense medium, slows down, the angle gets a bit sharper, it gets closer to the normal. See how this is why the normal is so important. The angle of incidence is in here. I'll draw it in for you. All right, that's I. This in here is your refracted, because it's next to the normal. That's why the normal is so important to draw. Okay, but if you can take a look down here, as we continue down, this top side, this is close to the normal. That refracted angle becomes our new angle of incidence. Okay, it flips around. That's our Z rule. You might remember from your geometry. Okay, and then again, that'll be the newly refracted angle as we go back into the new one, the old medium, I suppose. All right, we can see that visualized a little bit differently here. So maybe we've got air and it's going into water. We've got our angle of incidence and our refracted angle into water. Sorry, I need to put my laser pointer on. Angle of incidence of air, and it goes into water. That's the refracted angle next to the normal, that straight line. But that becomes the new angle of incidence when we go from water to glass. All right, and the same kind of process happens. This one becomes over here, and so forth and so forth. Okay, so you don't need to keep doing, 90 minus the new angle or whatever it is. Because of the Z rule, you find that refracted angle, and that becomes the new one. Okay, this is just a rearrangement of the formula I gave you guys the other day. I told you that N is equal to, and we called it VA over VM. VA was like the velocity of speed of light in air divided by the velocity of the speed of light in the medium. It's not a very good M. There you go. The other way that we write that is, well, the speed of light in air, we actually just call it c. That's the constant of the speed of light, c. All right, and then that'll be divided by the velocity of the medium. So we just call it v in our case. So that's where that formula comes from down here. Okay, so it's just a different way of rearranging it. I'm not too sure. I don't believe you guys have this on your formula sheet. It would be worth checking. And here's a couple of constants. So every single different medium, different property, so if it's a vacuum, if it's helium, water, etc., they've all got a different constant, okay? And that's the refractive index for them. Many of these will be listed in your formula sheets. I think that's really important in year 12s, is that if they just tell you, all right, a particle of light went from air into water, well, you can be like me and remember that air is 1 and then water is 1.3. But if it's something a little bit different, take a look at your formula sheet. I guarantee it'll be in there, okay, because it is a constant. Otherwise, they'll just tell you in the question itself. Okay. We spoke briefly about the critical angle. Year 11s, this is not relevant for you guys. Year 12s, it could be. But the thing is, though, is that this is not on your formula sheet, which makes me think that you would not be asked to calculate it, but you should be aware of it. And we spoke about the critical angle. This is where we only get reflection occurring. All right, if the angle of incidence is less than the critical angle, okay, then we get some refraction occurring. It goes straight through. But I gave you guys the example of when you're out at the beach and as the sun comes down, you can't see the ocean anymore. Instead, it's just glare bouncing straight back at you. That angle of incidence, all right, is past the critical angle. And so instead you get complete reflection instead. And all that light comes straight back at you instead of going into the water, allowing you to see down. Okay, so I think the idea of critical angle is important to know. It is only dependent on the medium itself. I don't think you'll be asked to calculate it though. Okay, refraction. Now I've talked about the bending of light itself, but light has got many different colors, I suppose. And all of those different colors have got their own refractive properties. So red visible light is 1.515. Orange, on the other hand, is 1.516, and so forth and so forth. And you may have heard of something called redshifting, the year 12s particularly. Year 11s will learn about it next year. And this is the idea that red light gets stretched longer because its wavelength is longer than violet, for example, which is a bit shorter of a wavelength. So it takes longer to spread it apart. That's important if we're looking at things like the expansion of the universe. This is how we know how far away different galaxies are, because we can see how much more red it is. So it's been stretched out further. Okay, and that can come down to its refractive properties. Okay, now we mentioned before that I can't go back, unfortunately. I don't know why that's a thing in PowerPoint when I'm recording, but whatever. We had that little drawing, and I told you that if something's being reflected down a mirror, okay, and you see some little object, maybe it's a ball, the distances are the same in the reflection. Refraction, on the other hand, is different, okay? You have all seen it before. We put like a straw into our cups, and it looks like the straw has been bent. Refraction completely changes the angle in our perception of the object. So for a diver, you might see him as really close, but in actuality, he's a little bit further down. Okay, we're now into Snell's law, being able to calculate that angle for ourselves. We did this problem yesterday, but I suppose I can quickly do it again. All right. First things first, I'm going to write down the information that I've got. So the angle of incidence is 25 degrees, and that's for water. So the angle is in water. It's going from water to glass. I also know that the constant for water is 1.3. Meanwhile, we don't know the refracted angle. That'll be in glass. Don't know it. And the refractive index for glass is equal to 1.5, just because I remember that from yesterday. We're going to write out our formula. Sine of I divided by sine of R is equal to N2 over N1. Now, I mentioned yesterday that normally we have all of the incidence first. And so you remember I can't go back, unfortunately. You've got incident on the top, you've got V1 on the top, lambda 1 on the top, and then we have N2. So another way that we could rearrange this, so it's a little bit easy to remember, is by cross multiplying. Okay, so we're going to have n1 times sine I, and n2, that's not a good 2, times by sine of r. And now this way, it's a little bit nicer to remember, at least for myself, because I've got both of those ones and those incidents on the same side, and the second refracted on the same side too. Either way, it doesn't matter. It's just another way we can help ourselves remember what goes where. So n1, that's originally in water. I suppose I should quickly draw this too. So we've got our two perspectives. We've got water up here, goes into glass. Okay, the angle is 25 degrees, and it's going to be refracted. It's more dense, so I suspect that it's going to be a little bit closer. Should be a little bit less than 25, I suspect. All right, so let's do some solving. N1, 1.3 times by the sine of 25 is equal to N2, which is 1.5, times by the sine of R. I'm going to divide by 1.5. That's going to leave me with sine of R by itself, because that's going to cancel out. So sine of R is 1.3 times sine 25 divided by 1.5. To get rid of the sine, let's see if I can erase this just to make it in one last step. R is going to be equal to sine inverse of all of that. And just because I remember from yesterday, R is equal to 22 degrees. And just like I predicted, it's a little bit less than 25. That's because it's going into a denser medium. So it's going to be slowed down, all right, 25, and then slowed down a little bit closer to the normal. So that's one way you can also verify your answer. If it was more than 25, but you knew that it was going into a denser material, well, you must have done something wrong in your math. Okay, hopefully that one makes sense, and there's another way of writing out the answer a little bit neater. Okay, a couple of different problems. I'll go through them with you guys, but please pause the video, try them for yourselves. Calculate the speed of light in a medium whose refractive index is blah, 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 blah. Okay, we're going to use that formula that n is equal to c divided by v. All right, so we're going to ask to find the speed of light. That's going to be the velocity, so v is going to be equal to c divided by n. All right, so we're going to have, I'm going to run out of room here, but that's okay. I'll let you guys do it. V is equal to, speed of light is 3 times 10 to the power 8. And n, well, that's 1.5. And then the next one would be 2.4 and 1.3. That's how it is. It's not too hard. All right, let's take a look at this question here. Calculate the refractive index for light passing from water into glass. Oh, no, sorry, these are two different problems. My bad. What are we doing here? Calculate the refractive index of the material shown. Okay, well, we don't know the material. N is equal to, we don't know it. And take a look, it doesn't tell you what air is, but we know that's a constant. All right, N is equal to 1 if it's air, which makes it pretty easy for us. We know the two angles. The angle of incidence is 65 degrees. The angle of refraction is 30 degrees. We're just going to use Snell's law. The only thing we don't know is N2. So sine of I over sine of R is equal to N2 over N1. And we just substitute and rearrange. Sine of 65, because that's our incident angle. All right, I is there, 65. Sine of R is 30. Sine of 30. N2, we don't know it, so I'm just going to say it's N2 over N1, which is 1. We're just dividing by 1, so it's the same as just doing nothing. And that makes it really easy for us, because that means that N2 is just sine of 65 divided by sine of 30. I don't have a calculator with me, so I'm going to trust you guys can do that one. Calculate the refractive index for light passing from water into glass. We don't have the drawing here. Again, I can't stress it enough. Draw the problem for yourself. All right, so we've got two different mediums. I'm going to draw that line of normal. We've got it going from water, so this is water. And again, that's a constant. N is equal to 1.3. We've got it going into glass. N is equal to 1.52. We're told that. Sometimes the question will give it to us. It'll be nice. We don't know the refractive... we're not even finding... Calculate the refractive index for light passing from water to crown glass. The refractive index. I'm going to suspect we're just going to be dividing those two. I'm not too sure what the question's asking. We'll look at the next the answers to that one shortly, actually, because that's Already given it. Let's do this last question, 7. This is a good question. Year 11's good question. A drop of soapy water. We've got n is equal to 1.38. All right, so that's going to be in this section here, 1.38. Was placed into a block of glass, which has got an n of 1.5. A ray from a laser was shone onto the light at an angle of 38 degrees. That's our incident angle. Determine the angle of refraction in the soapy water, and then the angle of refraction in the glass, the angle at which the ray exits, and the relative refractive index. Now, I've already typed these out, so let's just go to the next slide, and I hopefully can remember the question well enough to explain them. Yeah, okay, here we go. So question 6, just like I predicted, I suppose I just want you to divide those two answers. This is not a very typical question. This is just the ratio between the two mediums. Not very typical. You're more likely to be asked to find the actual constant itself, not the ratio between the two. But nonetheless, there we go. Question 7, first things first, let's draw out a diagram. So we've got 38 degrees coming in, and A was equal to 1 because it was in air. It then went into that soapy water, which is 1.38, and then it went into 1.5, and then back out into the air at 1. Okay, so we've got our angle of incidence to the normal, next to the normal. We've then got our refracted angle, which is next to the normal. But remember, because of the Z rule from our geometry, or you could go through the steps yourself, the refracted angle is going to be the new angle of incidence, angle theta 2. And then we can then find the next refracted angle, which again becomes the new incident angle. So let's go through the steps. Question A, it asks us to find theta 2, the refracted angle. Okay, so we have got it. There's probably not enough working out there for you guys to at least get started, so I'll help you out. Sine of I over sine of R. You're going to love this formula. We're going to do it again and again and again. Is going to be n2 over n1. And now we just start to substitute. Sine of I, that's going to be sine of 38. That's our incident angle. We don't know the refracted angle, so we're just going to leave it as R. N2, it's going into that soapy water, so that's 1.38. N1 is where it started. It started in air, which is just 1. Okay, let's rearrange that for ourselves. Hopefully you guys can multiply, divide however you like. I'm just going to I'll step it out for you. That's okay. Dividing by 1, that's not going to do anything, so let's just wrap that out. And I'm going to bring the sine of R up to the side. Because it's currently being divided by sine of R, let's times it out. So sine of 38 equals 1.38 times sine of R. Alright, we want to get sine of R by itself, so I'm going to divide by 1.38 on both sides. That's going to cancel it out. Okay. I've just screenshotted this from the answers, but I can already see there's a bit of a typo here. All right, they're saying it's 0.4, that's sine of 38 divided by 1.38. But then take a look at this. We're trying to find R. So to find R, we're going to do the inverse sine of sine of 38 divided by 1.38. Okay, they're telling us 0.4. But then they've just set it 0.45. So sometimes the answers are wrong, which I suppose I'm glad that I stepped it through with you. Whatever the answer is meant to be. If it's 0.4, you're going to, or you could just type it in like I've done here. The inverse of sine 38 divided by 1.38. That's going to give you the refracted angle. They think it's 26.49. Let's not always trust them. We've just seen that they made a mistake here somewhere. Okay, so this angle in here, let's call it 20. I'll just round it up to, or round it down, I suppose, 26 degrees, which means this new one is 26 degrees. Wonderful. So then if we wanted to find the next refracted angle, okay, I will get us started. We just do the same thing. Sine of I over sine of R equals N2 over N1. But now our incident angle is 26 degrees. Sine of 26 over sine of R. We don't know the new refracted angle. The refracted angle is going to be theta 3 in this case. N2, that's what we're going into, which is 1.5. And N1 is where we started. We're starting in that soapy water, which is 1.38. And we do the same math. We rearrange it the exact same way. which they think is 24.2. Check them to see if they're right. We've seen them wrong again and again. But nonetheless, that's how we go through that. And you just keep repeating those steps until eventually you find out what that bottom angle is. Now, I've got my face in the bottom right-hand corner. Let's see if I can move that. Can I hide my face? I can. Okay, there we go. Now, they've said that the final angle is 38 degrees. That does not always happen. That is all I will say. That does not always happen. You need to go through the steps of finding the different refracted angles. Okay? That's where I'll leave it. Year 12s, definitely go through the steps of finding all the different refracted angles. And I've got a blank slide, so that is it. Guys, I hope that that was helpful for you. Just to recap, we learnt about ray diagrams. The angle of incidence is equal to the angle of reflection. Whenever you're making a ray diagram, the angle of incidence is next to the normal. All right, the angle of incidence is next to the normal. The angle of reflection is equal to the angle of incidence. And when you do the refracted angle, I'll call it theta r. It is also next to the normal. Okay, these are both next to the normal. Okay, and then we also had a bit of practice with Snell's law. All right, I hope that was helpful for you all. Feel free to do those other simulations, and I will see you guys on Friday so we can do our experiment, which will be calculating the refractive index of a certain material. All right, have a good one, everyone.